this is an extra lesson on rates of reactions. This is the first time that we start looking at the way chemical reactions happen and the speed at which they happen. Until now, what we've been taught or what we've learned is that when two substances react with each other, we write it down, we write the chemical equation, and we just assume that it happens exactly like that. Whereas in reality, it is not that simple. It is not always as simple as just adding hydrogen and iodine into a container together and expecting that they just react and all of it forms hydrogen iodide. So in order for us to start to understand how these reactions happen, how quickly they happen, and what affects the rates at which they happen, we need to understand something called collision theory. So what collision theory is it essentially gives us a guideline for how we judge how successful a reaction is going to be. So there are a couple of principles that collision theory is based on. The first one is that in order for a successful collision to occur, there are two, or we could see it as three, requirements that must be met. The first one is that if we look at these two particles over here, we've got a hydrogen molecule that's made up of two hydrogen atoms and an iodine molecule that's made up of two iodine atoms. So the first condition that must be met is these two particles must collide with each other. If they do not collide with each other, if they don't get close enough to form new bonds and break the old bonds, there can be no collision. So our first condition for collision theory is that the particles must collide. The reason why collision is not so simple is because the center of each atom we know contains the protons. The nucleus contains the protons and the neutrons, and then around that we have the energy levels with the orbitals that contain our electrons. So what that means is that surrounding every atom we essentially have sort of a negative cloud of electrons. And the result of that being that these molecules tend to repel each other because there are those negative clouds that come into contact with each other before anything else. So the second condition is that when these two particles collide with each other, they need to collide with enough energy that they overcome that repulsion. Right? Those negative forces that are repelling them need to be overcome, which means that these particles need to come in with enough energy to be able to break through that and get to the point where the particles actually collide with each other. Right? So they need to overcome the electrostatic forces of repulsion. Now the next problem comes in with how they collide. Because as you can see here, if these two particles collide and collide with enough energy, but in that orientation, no reaction can take place. Reaction can't take place because we need this to be able to split into a hydrogen and iodine, combine with each other, and a hydrogen and iodine. What this would split into, if it were possible, is a hydrogen iodide molecule and then a separate hydrogen and iodine that go off in their own directions. So the third condition for collision theory to be met is that they need to collide with each other in the correct orientation. So collision theory very simply says that in order for a reaction to occur, we need three things. One, we need the particles to collide with each other. Two, we need them to have enough energy so that they can actually get close enough for that collision to be possible. And three, they need to collide in the correct orientation. What you'll see here is a commonly misunderstood thing. We always believe that when a bond was formed, it happened where somehow these two hydrogens just drifted apart, and then the two iodines drifted apart, and then they, by some miracle, found each other in space to form hydrogen iodide molecules. That is not the way that this happens. The way that it happens is through this collision that forms something that we call an activated complex. An activated complex can be seen as the in-between phase between our reactants and our products. It's called an activated complex because it is unstable. But you cannot just force four atoms together and expect that to be stable and stay like that. So we call this the activated complex because it is an unstable state that is existing briefly between us having reactants nice-forming products. So this entire section is based on collision theory. This entire section is based on how can we change the way in which these particles collide with each other to affect the speed at which this reaction happens. Right, so once you understand this, you can already start to see that there are a couple of ways in which you can make this happen a bit easier. You can already start to see that because the energy matters when they collide, if they have more energy, they would collide more often. So therefore we can say, oh, well, temperature is directly proportional to energy, so if they have more energy, or if there's a higher temperature, therefore more energy, we would have more collisions. Right? We can also see that if we force these particles closer together, either by changing the volume or by increasing the concentration, we're making them collide more often with each other, thereby making a successful collision more likely. Right, so that is what this whole section is based on. There are some very few calculations that are possible here where we are actually asked to calculate the rate at which this reaction happens. The formula is very difficult to define because it depends what you're asked for. In this case, if hydrogen and iodine are all gases and hydrogen iodide is a gas as well, then it can be the change in concentration over the change in time. But if you're reacting a solid with a liquid, you could have the change in mass over the change in time. So whatever is reacting, as long as you're measuring what it changes by, so whether you're measuring the change in the number of moles, or the change in the mass, or the change in the concentration, or the change in the volume, and dividing that by the time, you are giving some kind of rate of reaction. The other thing that I hope would be clear here is that the rate at which your reactants decrease, we know the reactants are what we start with, the rate at which the reactants decrease is going to be directly proportional to the rate at which the products increase. Because if I use up one molecule of hydrogen, I cannot do that without automatically forming a molecule of hydrogen iodide. So when you're asked to calculate a rate, it often doesn't matter if you're calculating the rate at which reactants are used up or products are formed, because the result is the same thing. You're essentially measuring how quickly that substance or that amount is changed. Right, what we're going to look at now is systematically the various factors that we can change that will change the rate at which a reaction happens. Right, so this again is all done against the backdrop of collision theory. The last thing that needs to be said here is that very few collisions are successful. So if we put a container in here that contains, let's stick to the hydrogen iodine example, that contains a whole bunch of hydrogen molecules along with a whole lot of iodine molecules, you need to accept that a lot of the time they are going to collide and one or more of the conditions is not going to be met. Whether it's because these two collide and they're in the wrong orientation, or because these two collide and they don't have enough energy, there are going to be hundreds of thousands, or strictly speaking millions and billions of collisions here. And it is only very rarely that one of those collisions is successful. So in rates of reaction, we're often going to be talking about two things. We're going to be talking about the number of collisions. Before Twitter, this was called a hash. And it represented a number. Right, so the number of collisions, and then we're also going to be talking about the number of successful collisions. Where you need to understand that the number of collisions is far greater than the number of successful collisions. Okay? There are literally hundreds of thousands of collisions happening for every one successful collision. Right, so we can start looking at the factors that affect the rate. The first one, we call it the nature of reactants, where nature of reactants here refers to essentially the phase that those reactants are. Are they solids, are they liquids, or are they gases? The reason why that matters is because it depends how easily particles can collide with this. So for example, if we have a container here that contains a piece of solid carbon dioxide, the only place where collisions can happen is on the surface of that carbon dioxide. All the millions and billions of particles that are trapped in the middle of that solid cannot collide. So when we have a solid, our number of collisions is going to be dramatically lower. Because the number of collisions is lower, the number of successful collisions is going to be lower. Right? We can then extend that logic to say, if we have a liquid substance, with everything now slightly more free to move, you are going to have more collisions because things are actually moving around, and you're far more likely to meet someone if you're moving around and not just standing in the corner. Right? So, your number of collisions increases as you go from solid to liquid because the particles are moving around, there's more chances of collisions. And then once again, that number of collisions increases, the number of potential collisions increases even more dramatically if you go from liquid to gas, because now it's not even bound by gravity and these particles can move pretty much anywhere that they want. And what's important to remember from the particle model of matter is that the particles in gases are moving faster than the particles in liquid. Remember that the phase is directly proportional to temperature, so as you move up a phase, you're increasing the temperature of those particles, and so your collision theory then says each of those particles has more energy when it collides, and therefore is going to be more successful. So the first factor that affects the rate of reaction is the nature of reactants, and the reason we say that is because the nature of reactants affects how much energy they have and how they move around and how many collisions we can have. Right, so very simply, the way that this can be asked to you is you're asked to compare the rate at which, say for example, zinc reacts with hydrochloric acid, and you're asked to compare zinc reacting with solid, so let's say liquid hydrochloric acid, and you're asked to compare that to how it reacts with gaseous hydrochloric acid. Okay, now pay attention to the way that we answer this. You say, this reaction is going to occur faster due to the nature of the reactant because it is a gas. The particles have more energy and more freedom. Okay, so the first thing you're doing is you're explaining why the nature of reactants is important. The next thing you're going to do is you're going to relate that to the number of collisions. So you're going to say because they have more energy and freedom, the number of collisions is going to be greater than in a liquid. Once you've done that, you can say, therefore, since there are more collisions, there will be more successful collisions, and therefore the reaction will occur faster. Right? It is a common place where we fall short, where we forget one of these two. You have to first explain why it affects the total number of collisions, and then take us to, therefore, it affects the number of successful collisions. So that's the nature of reactants. Next one is the surface area. This refers mainly to solids, where if we look at our example, if we want to react a piece of zinc, if this is the piece of zinc that we need to react with hydrochloric acid or whatever the case may be, the reactions can only happen on the surface of that solid. So if I were to cut that in half, right, I haven't changed the amount of substance at all. What I have done though is I've added an extra surface on which collisions can happen. So as you continually make this smaller, you're increasing the surface area. Which is why when you're asked to compare zinc chunks, I think chunks is the word they use, to zinc granules, to zinc powder, what you need to see is that the finer we grind it up, the more surface area there is. Because there's more surface area, and then we follow the same steps here, because the surface area is greater, the number of collisions is greater, and since there are more collisions, there will be more successful collisions. Therefore, zinc powder would react faster than zinc granules or zinc chunks. The third one is concentration. Again, pretty much the same thing here, where now you've decided you're going to use zinc granules. So you've got your zinc granules floating around here, and you've got something, hydrochloric acid, that is dissolved in water. So the volume here is set. So it's 1 cubic decimeter, which is just a fancy way of saying 1 liter. The volume is set. So if I decide to increase the number of molecules of hydrochloric acid, thereby increasing the concentration, I'm increasing the number of times that hydrochloric acid is going to collide with zinc molecules. And then, once again, because I'm increasing the number of collisions, I'm increasing the number of successful. But what you should start to see is this all actually becomes very repetitive, right? As long as you understand what the initial effect is that leads to an increase in an increase in collisions, then the rest of it is pretty simple. The next one is pressure. So essentially, you know that if we took the same container, if it was a gas now, and we compressed it to half the volume, that automatically doubles the concentration, because concentration is the number of moles divided by the volume. So because I've compressed it, I haven't changed the amount of hydrochloric acid that's present there. All that I've done is I've said, instead of dividing by 1, divide by half, and so I've increased the concentration. Okay, so concentration and pressure are pretty much the same thing, in that both of them lead to there being more particles colliding, more collisions, therefore more successful collisions, etc. Right, temperature is a slightly different one. The reason for that is that, strictly speaking, the definition for temperature is a measure of the average kinetic energy of all the particles present. Right? You remember, I think, that we did a graph like this in grade 11 that showed that if you say that the average temperature for a glass of water is 25 degrees Celsius, that does not mean that every particle in that glass of water is 25 degrees Celsius. What it means is that most of the particles are around 25 degrees, but there will be some that have incredibly high energies. There will also be some that have very low energies. Right? This explains why evaporation is possible, because even though the water isn't boiling, there are a small fraction of particles that have enough energy to be able to escape and become a gas. Right, so when we're talking about temperature, you need to understand that we are actually talking about a spectrum here. We're saying that, yes, the average temperature is 25 degrees, but that means that all of their temperatures can be quite different. So, the effect that this has is that when we increase the temperature of a container, we are increasing two things, which is why temperature has such a big effect. Okay? Temperature increase does two things. One, it increases the kinetic energy, which you remember is directly proportional to the velocity of those molecules. Right? So when your velocity increases, it means these particles are bouncing around far more, and since they're moving around more, they're more likely to bump into someone and more likely to have a successful collision at that. The second reason why a temperature increase affects your rate of reaction is because a temperature increase means that every single particle has more energy, and if we go back to collision theory, we said that in order for a collision to be successful, the particle needs to have enough energy to overcome the force of repulsion. Okay, so a temperature increase has a twofold effect on the rate of reaction. One, they're moving around and colliding more. Two, more of the collisions are successful. So your answer here is slightly different, because now you're saying not only are there more collisions because they're moving faster, but the number of successful collisions, or the proportion of successful collisions, is also higher. Right, and then the last one is a catalyst. Now a catalyst does a completely different thing there, where everything else that we've dealt with has first increased the number of collisions and then increased the number of successful collisions. What a catalyst does is it provides a shortcut. Okay, so if we go back to our example of the hydrogen and iodine atoms, what a catalyst does is normally a contact catalyst, is it normally forces the substances to stay in a certain position. By staying in that position, it guarantees that another collision is going to be successful. So unlike all the other things that we've had, where we've said they all increase the number of collisions and therefore the number of successful collisions, what a catalyst does is it just increases the number of successful collisions. Right? So if we were having 100 collisions and getting 10 success out of it, a catalyst just makes it easier and says, well, now 20 of those collisions are going to be successful. Right? So the catalyst is sort of the outlier here. So once we understand the factors that affect the rate of reaction, what we can start doing is looking at the two ways in which reactions either gain or lose energy. So the first type of reaction that we have is called an exothermic reaction, where we plot this, or we show this on a graph that plots the potential energy of the agents present, those being reactants and products, and it plots those against, now normally what we would say is time, but because this is happening so quickly, what we do is we call it the reaction coordinate, but it's just a fancy way of saying time. So we know that bonds form in order to achieve stability. So when we're using our example, let's go back to the original example, hydrogen and iodine to form hydrogen iodide. What we can say is we can measure the potential energy of our reactants, in this case being hydrogen and iodine. Now, assuming that we have a successful collision here meaning that the particles collide, they collide with enough energy and they collide in the correct orientation. They temporarily form something called an activated complex, right? So this over here was when there were two separate molecules. The activated complex is that conglomerate of both molecules jammed together, and as we said, it's a very unstable state, it's also a very brief state, which is why the potential energy increases, meaning the potential for this to break apart increases dramatically. Now, at this point, a reaction can do one of two things. A reaction can either be exothermic, which means that hydrogen and iodine would rather be with each other in the form of hydrogen iodide than they would be separate. The way that we show this is we show that hydrogen iodide has a lower potential energy, therefore is more stable. Right? When we show this line below here, what we are saying is that the potential energy of hydrogen iodide is lower than hydrogen and iodine. Therefore, this form of the reaction is more stable. Now, because it's more stable, that means that there's a certain amount of energy that is not needed anymore. The energy that was used to keep those two molecules together is not needed because of this new stability. This over here is called the enthalpy. Now, enthalpy we can simplify to calling it the heat of the reaction. Essentially what we're saying here is we are saying that this reaction is giving off energy. Every time hydrogen and iodine molecules collide with each other to form hydrogen iodide, they give off a certain amount of energy. Now that energy enters the system. So we see this as the system heating up. Every collision gives off energy. That energy goes towards heating up the entire system. We call this type of reaction where the enthalpy change is negative an exothermic reaction. Exothermic because it gives off heat as the reaction proceeds. The opposite of an exothermic reaction would be one where the products that are formed are less stable than the reactants. Okay, I'm using a random example, I'm not sure that this is correct. The reaction between nitrogen and hydrogen to form ammonia, so I'm pretty sure this is correct, where nitrogen and hydrogen are more stable in that state than in this state. So the only way that this can happen is if energy is absorbed. energy is required to make this reaction happen. So what we see here is the enthalpy change is positive, which means that this has to pull in energy from the system. So what we find is that energy is being removed from the system, so we say that the reaction cools down. The reaction mixture cools down. Right, so that is an endothermic reaction. A couple of things that we need to point out. Here, the first, the amount of energy that is required to get us from the reactants to the activated complex is called the activation energy. It's the amount of energy required to start the reaction. So this is going back to that amount of energy to overcome the electrostatic force of repulsion, called the activation energy. You'll see that the activation energy in this case is given there. It is always from the energy of the reactants to the activated complex. Now this allows us to explain what a catalyst does. What a catalyst does is it lowers the required activation energy. So where, say, 10 joules of energy was required to start this reaction without a catalyst, with a catalyst, we're providing a shortcut that gets us to our products faster. So we can see here that the activation energy with the catalyst has decreased. Okay, and that explains then why the collisions become more successful, is because less energy is required to make the collision successful. Right, so that is our exothermic reaction, the endothermic reaction, and then there's a definition for the activation energy. Minimum energy needed for a reaction to take place. Note there that the units are in kilojoules per mole, meaning that many kilojoules are required to make a mole of substance react. And then the last one is the definition for reaction heat, or also known as enthalpy.